And as Diana mentioned before, my name's Dr. Craig Bowers, and I'm a volunteer here at the Perth Observatory with their group, as well as being the honorary historian to the Perth Observatory, which was an honour bestowed on me by the Department of Parks and Wildlife, which I appreciated very much. On top of that, during the long distant past, the 80s, I was an astronomer here for the 1980s and came back for a short period in the mid-90s. The Perth Observatory existed, has existed, as everyone knows, since 1896. And it's had a checkered life, shall we say. It's seen 2 world wars, it's seen a Great Depression, and it's had several unsuccessful attempts to close it, mostly been thwarted by yourselves, the members of the public. And in around about the mid-1950s, the land around Perth was being looked at for development, as we always do. And a proposal was put forward to put, I think it was 4 or 5 government buildings on the top of the hill where the Perth Observatory was at that point in time, which was directly opposite the entrance to Kings Park. Luckily, we only ended up with one monstrosity, which is Dumas House, which most people will recognise today. By the early 1960s, there was a decision to a suggestion to either close the Perth Observatory or to relocate it. And luckily, we got it relocated to the Darling Ranges, and that commenced in the early 60s. It was a great place to be. It had actually been investigated before as to a possible location. And the relocation, well, the first few years, the probably first 50 or 60 years of the observatory has been documented very well by my predecessor, my historian predecessor, Dr. Muriel Utting, and she has 3 volumes which take you from 1896 through to 1960, and they are available in the shop as well. It's a really good read to hear or to read exactly what happened in those days and some of the challenges. Anyway, after the relocation took place in the 60s, the services that were provided by the Perth Observatory in the first probably 50 or 60 years were really particularly services. They were designed to provide information to members of the public: sunrise, sunset, tables, tide. We used to set off the gun the cannon to allow people to set their watches. But when we moved up here to the Perth Observatory in Bickley, that kind of changed a little bit, and the institution moved to more science or research. And this started really when the domes were being built, the land had been cleared, when an expedition arrived here from the Hamburg Observatory in Germany to set up a telescope here at the top, the hemispherical telescope there, the Meridian. And 3 couples came out and lived here for some years, about 3 or 4 years, to create star catalogues. At the same time, around about time, the old astrographic telescope from 1899, when it arrived in Perth, was refurbished and put in another dome here on the site. And at the same time, as you'll hear a little bit tonight, an observatory in America, Flagstaff, Arizona, brought out a 24-inch telescope and located it here. And similarly, the University of Western Australia wanted to get involved in astronomy at that point in time, and they erected the telescope with the dome just up to the side here. So there was a lot of astronomy going to be done over the following years. As Diana's pointed out, I did write a book for the 50th anniversary of the Perth Observatory, and that's, again, sales pitch at in the shop, and the extremely interesting read. I'm currently writing out of my PhD, which, as Diana pointed out, has been bestowed on me today, which I'm very grateful for. Thank you very much. It's been a very long road, and I've read a lot of old volumes, I must admit. It's been very interesting, and what I'm hoping now to do is take that PhD and create volumes 4 and 5 of the history of the Perth Observatory, taking it from around about 1958 through to 1993. Over this point in time, I'd like to say the Perth Observatory has made many discoveries since relocating to Bickley. Some of them which have really changed the theories that were held at that point in time in history. They were significant changes, and they really rocked what we thought about our solar system and beyond. And you'll hear one of those, I suppose, those turning points in life tonight with Peter's talk. So while starting at the Perth Observatory just after it moved here, Peter was one of the major contributors to the discovery that we're going to hear about tonight, as well as one of the core people for the outreach and public relations within the observatory's gambit for over 40 years, and that's a fair bit of time, that is. I've been very, very lucky to have had Peter as my mentor in the beginning when he took me on board and weaned me into the 24-inch telescope when I was on a Meridian observer, which wasn't exactly the most glamorous of jobs at that point in time. But more importantly, I've been lucky enough to be Peter's friend for 35 years now. So on that note, I'd like to shut up and pass over to your speaker tonight, Mr. Peter Birch. Thank you very much.
I'm lucky that we could do this tonight. I'd like to tell you a story tonight. We're going to go back to the 1970s and tell you a story. Just as an aside, no, you can turn that off, Matt. I don't need that. Just as an aside, my son Matthew's birthday is March the 10th. And no, we're not going to sing happy birthday to you, Matt, but he's always been rough on me because I never attended his first birthday in 1977. So Matt, this is a story tonight about what I was doing on your first birthday. So the way I'd like to run through things tonight, and I hope you can all see these things on the screen, I just want to talk about what it was like to be at Perth Observatory in the 1970s. I'll go through how the largest telescope was actually established here. I'll talk about a new word for a lot of people called occultations, because this is what happened with the planet Uranus. And I'll talk about the Uranus event and where we went from there and how we actually ended up with something that was quite important in the end. So in the 1970s, it was pretty exciting to be in science. The space race between the West and the nasty old Russians was on. Satellites with humans were going into space. How many people here tonight are older than 48 years? You know, there's probably a lot that aren't. And those people that are, can you remember what you were doing on the day man landed on the moon?
Exactly.
And thank you. Everybody can remember what they were doing the day man landed on the moon. So in the 1970s, there was all these things that were going on. And computers were just starting. The first, hang on, we'll push this one and it'll go again, maybe. The first little computers we had were things like a Commodore 64 and the Atari 520 SE. And spacecraft like Voyager, which is right out near the edge of the solar system, were powered by computers of this sort of calibre, something like the Commodore 64. How good is that we could do that so far in advance? So Perth Observatory in the 1970s. Star positions, basically. A Meridian telescope taking positions of stars as the stars moved across the sky. Glass photographic plates, dark room, a long, tedious process. And how did we get information? Well, we had telegrams, which we used to send. Remember telegrams? We used to... Thank you. And how did we get astronomy news? It was tough. It was tough going in the 1970s to actually find out what was going on. And just as an example, if I can make this thing click over. Matt, why isn't this thing clicking over for me? Here we go. I don't know how well you can see that, but this is an example of an astronomical telegram. A piece of paper with a whole lot of numbers. And these numbers, you read from the numbers what the information was, and at the end there was a number called a checksum. And you added all the numbers up, and if they added up right, they came to the numbers at the end. So that's the sort of way we used to bandy about information. There were no mobile phones. William, my grandson, couldn't live without his mobile phone.
No, I could not.
There was no internet. No internet. Can you imagine not having the internet? The astrographic telescope, pretty much as it is now. The Hamburg Transit Telescope is now gone back to Germany. There was a 16-inch reflector telescope there. There was the computer, the first computer at Perth Observatory had a 1K drum store. And that was about the size of 2 large refrigerators. It was run with punched paper tape, rolls of punched paper tape. So none of the technology we know now was in service at that time. Perth Observatory did these sorts of things. There was sunrise and sunset tables. Once a month, if you were privileged, you could come to Sunday visitors at 3 o'clock on the first Sunday. Legal advice, we did that sort of thing where we stood up in court and said the sun rose at such and such a time, and therefore you should have had your lights on in your car and when you had an accident, that sort of thing. So let's just talk about why is Perth Observatory here? Why is Perth Observatory out here in the bush, away from Perth? The main reason is to get away from the city, to get away from city lights. It's pretty inconvenient having an observatory so far from the city, but you can't do both. You can't have the observatory in the city. An example of that is in Sydney, where the Sydney Observatory is right next to the Sydney Harbour Bridge. And, you know, it's not really much use as an observatory there. Also, the air is up, we're up a bit higher because we're in the Darling Ranges, so the air's a bit more stable. Perth Observatory is very isolated. The next observatory, if we go west, is in South Africa, and if we go east, is in New South Wales. So, why did the United States want to establish an observatory here in the 1970s? The basic program that set this up was to obtain coverage of the planet Mars. Because in 1971, Mars came very close to the Earth, and I'll talk about that in a minute. Lowell Observatory had a big NASA grant. They also put telescopes in these other locations like South Africa and Chile and Hawaii. But our unique latitude and longitude was a long way from any of these other ones. So that's why the telescope was established here. The other reason was stable politics, although you've got to wonder about that after this week. Really? And the whole process of putting in this bigger telescope was paid for by the NASA grant, so it didn't cost the West Australian taxpayer anything to have this done. Why in 1971? Well, Mars in 1971 was coming the closest that it came to Earth for 70 years. And the NASA space mission was planning missions to Mars, and they wanted to make maps of the surface of Mars. How do you do that? Well, you take lots and lots of pictures and you put them together, and that's what the original program was in the early 70s with this telescope was meant to do. So the surface maps for Mars were taken, hang on, I'm getting ahead of myself here. The surface maps of Mars were taken from these telescopes around the world, and the Perth Observatory telescope was in the top 3 of these telescopes that they put out as far as results go. The large image that we were able to get of Mars through the telescope was due to the fact that Mars was close. And for those of you that look through telescopes, Mars through the telescope in 1970 was about half the size of Jupiter. And if you look at Mars through a telescope normally, it's much smaller than that. Well, this is, I don't know how well you can see these at the back, but this is basically in 1971. You've got the dome. Some of you have seen the dome with the lid being put on it, and a couple of fresh-faced astronomers here watching it all happen. So this was put together in 1971. The telescope was all analogue. There was no computers involved. It was all just pushing hand buttons. It meant that you had to know where the telescope was pointing in the sky. You had to be able to look through the eyepiece and recognise where things were. You had to set these dials at the front of the telescope. You had to set these dials every night to go and find the stars that you wanted. So this was how the telescope started. It is now fully automated thanks to people like Andrew Williams. It's now fully automated and runs through computer control. But that was the way we had it in the 1970s. Now, I put this picture up just to show you how handsome I was in the 1970s. But there's a couple of things that are actually relevant on this picture. If you look at my tidy desk, where is the computer? There's not a computer on the desk. A couple of things that you can see here at the front, there's a green packet. That's a packet of film, because in the 1970s we took photographs on film. You can see these blue boxes back here. These are boxes from binoculars that we actually use binoculars to look at the sky. The only other thing of note on the table really is this old telephone, because that's really all we had for communications with. Okay, so we ran, in the early 1970s, we ran a thing called the International Planetary Patrol. And we took photographs of Mars, primarily Mars, but also Jupiter and Saturn when they were available. Each night we'd take pictures on the hour through various filters. So we take a sequence of filters every hour. The film we'd send off to NASA every 3 days. We developed some of it here to make sure it was working okay, but most of the film was sent away, and maps were made from this film that we actually sent away. These are some of the maps or pictures that they came of Mars, and this was in 1971, just to show how good we were at the observatory. In the top 16 that were taken around the world, we actually had the one at the top and the one at the bottom. We actually had two, even though other observatories like on Hawaii were at 10,000 feet above sea level, we were able to compete, and we proved then that the site of Perth Observatory was as good as any for actually getting things done. Now, one reason they were looking at Mars with the Viking missions going there was to map the surface, and this was mapping over several days of the dust storm that developed on Mars. From pictures taken at Perth Observatory, you see Mars here with various features. A dust storm develops, and then after about 15 days, it's completely blanked. And this is what we're able to do, take lots and lots of pictures of Mars. Jupiter also, but Jupiter was really never as changing as much as Mars, and Mars was the main priority. So we proved with this program, with the new telescope from NASA, that we could actually do things at Perth Observatory. The next stage that we got to in the development of astronomy in the 1970s was doing something called photometry. Now, a photometer is something that's used to measure light intensity. And if you can measure how bright something is in the sky, you can tell things about it. And how the brightness changes, you can tell things about it. So the photometer is actually on a desk inside. Some of you will have seen it tonight. I've shown a couple of people. So this was quite a big change for us, going from photography to photometry. Almost as big as the further stage when we went to CCD cameras probably 20 years later. So the photometer on the back of the telescope, it's hard to find decent photographs of this thing, but this is the telescope here, and I'm sure a lot of you have seen the telescope with the photometer on the back. It's blue. Have a look at it inside on the desk at the museum. It actually is a lovely old instrument. So we proved in about 1974 that we could do things with this photometer. We could actually measure the brightness of things with the photometer. And these were some of the first things that we published, and their changes in the brightness of the moons of Jupiter. At the time, it was a project that was going, and we joined in. We then did things like light curves of asteroids, how the asteroids change. In the 1970s, the number of asteroids, probably 1971, the number of asteroids that had been discovered was probably about 3,000. The number now is like 600,000. So exponential change in the way they dealt with asteroids. So we actually found quite a lot of asteroids at Perth Observatory. So as asteroids move through space, they tumble and turn around. They're odd-shaped bodies. This is a particular one called Gaspara, and you can see it's longer than it is round, and it tumbles and it changes light. And as you watch these things, as light changes in the sky, you can tell things about objects. And this was some of the light curves we made of a particular asteroid. So for a couple of years there, we were learning to do stuff and learning to use the photometer. I'm heading towards what we did with the rings of Uranus eventually, but I need to just go on this roundabout journey just to let you know why we did some things. A new word to a lot of people would be occultation. And an occultation is just like an eclipse. It's when one body moves in front of another and blocks the light out. So when you get the moon moving in front of the sun and you get a solar eclipse, that's an occultation. But in astronomy, we tend to use it more for distant planetary bodies and stars. And so when a planet moves in front of a star, the light from the star gets cut off. And we can measure the light from the star and the body of the planet. And that gives us all sorts of information about the star and the planet when the light is cut off. So with the planet Uranus, in the early 1970s, not a lot was known about Uranus. And Gordon Taylor from England and an astronomer from Lowell Observatory, Larry Wasserman, predicted that the planet Uranus would move in front of a star. Now, why is that valuable to astronomers? Because we can actually watch the starlight as the planet goes behind the star and see how much the atmosphere blocks out the starlight. And that was the plan with this event that happened on the 10th of March 1977, was to actually watch the starlight as Uranus went in front of the star. Now, there was a lot of doubt as to where this event would actually be visible from. The first prediction was that it would be visible all over Earth. And as they studied it more and more and took more and more positions, it proved that it was only going to be visible from the southwest of Western Australia and out over the Indian Ocean to the south and west of Perth. So Perth Observatory was the only observatory in the world that was going to be able to observe this event. How good is that? People say Perth's so isolated and we're so far from anywhere. Well, this was one time when that was a real benefit to us. I don't want to dwell on this slide for very long, just tell you that Uranus is a lot bigger than Earth, 25,000 kilometres in radius as opposed to 6. It goes around the sun once every 84 years or so. And at that stage, we knew that Uranus had 5 moons. Never heard of rings. We knew that Uranus had 5 moons. This event became a very high priority with NASA because they didn't know anything about the atmosphere of the planet Uranus. So lots and lots of observatories took positions on glass plates, which had to be then measured. And as the objects got closer and closer, it became more and more evident that all the rest of the world was going to miss out. It was only going to be visible down here and over the Indian Ocean, as I said. It was so important to NASA that they mobilised their C-141 jet, which was a huge aeroplane with a telescope sticking out the top. Now imagine this, if you will, is a big aircraft like this with doors that open and a telescope pokes out the top of the aeroplane. This aeroplane's probably flying at 500 kilometres an hour, 35,000 feet above the Earth, and just let me go back there. And you put a telescope out the top. How are you going to watch a star? With great difficulty is the answer. And they had some, at that time, 1977, they had, computer stuff that could actually do that. So this was the sort of jet that they sent from NASA down to Perth to actually observe this event. It was called the Kuiper Airborne Observatory. It had a 36-inch telescope that stuck out the top of it. The idea is the telescope remains fixed on a star as the aeroplane flies along. And they can use this to follow the area where the star was going to be behind the planet Uranus. So the star was going to move in behind Uranus no matter what, but in this aeroplane, they can actually fly along and actually see it go in behind Uranus and go out again and change their track as they need it. Something that we couldn't do from Perth Observatory because we're stuck on the ground. Okay. Well, as we built up towards this event, Dr. Mellis from Royal Observatory came down here early in March. He bought a special photocell to go on with our system that we had. The technicians got to work on the telescope and greased it all up and pumped up the dome tyres. And we were all primed for this event because there was a lot of publicity had gone into it science-wise as to how important it was to work out what the Uranus atmosphere was made of. We held a meeting when the Kuiper Airborne Observatory arrived in Perth. We all went down there and oohed and ahed at all the fancy equipment they had and sort of talked about how we were going to manage our observations. Well, come March the 10th, the last positions had been taken. The final actually predictions had been made about what was going to happen that night. So we sort of had a sleep in the evening and assembled up here at midnight, turned the telescope on, and we could actually see Uranus was getting quite close to the star. So from starting at about midnight, we could actually see that the two objects were getting closer and closer together in the sky. So at the telescope that night, we had Dr. Mellis and myself and a technician, Dan Trout from Perth. We had a paper chart, and if you have a look at the data recording system inside, you can see the paper chart. And we had a digital magnetic cassette tape. Now, you all remember cassette tapes? No. Well, this was before CDs and before digital stuff on computers. We had a 1 minute time beep. So every 1 minute we'd get a little tick on our chart or a little beep on the tape. As the data was being taken, I would actually write down on a piece of paper the actual numbers that were coming out of it. Every 10 seconds we got some numbers and we'd write them all down. So it was pretty basic what we're doing. This is not recording it on a digital computer for playback. This is really basic stuff. The data recording system, some of you will have seen it inside, and this is the paper chart unit that's here. This unit here recorded, we took the red numbers off, and basically there's various plugs. This was made in about 1971 just to fit our photo cells. So we started taking data at about 4 o'clock. The predicted times were just before 5, and I'll get to them in a minute. But we thought, well, let's give it a lot of time. We'll start at 4 o'clock, and so we're going to have lots of time. After about 10 minutes, our signal disappeared, and then it came back again. And we thought, what's going on here? And then it disappeared, and then it came back again. And at this stage, the star was still quite a long way from the planet. So we scratched our head at the time, and what's going on here? Well, we don't know, we can't solve it. Let's just keep on keeping on. I know you can't read this bit of paper, but it's a copy of, it's just an A4 sheet with the time and the numbers. The time and the numbers. And this is at 10 past 4. We've made comments here that there's something strange about the readings. And we just kept on recording, and there's about 10 pages of paper after that. So by about 4:30, we're thinking something's going to happen soon that we expect. So the initial prediction made by the Englishman was for 2048. That's 4:48 in the morning. And we didn't notice any change in the signal at that time. The second prediction was a bit later, and then we didn't notice anything there either. So the star was then supposed to be directly behind the planet Uranus at 3 minutes past 5 in the morning. And by that time it's starting to get light, and the usefulness of what we could do was starting to decrease. By 5:30, 21:30 UT, it was too light for us to continue. Put the eyepiece in, and the star was visible above Uranus. Well, what's happened here? Why did we get the data dropping? Why didn't the star go behind Uranus? Basically, the positions that were done and the orbit of Uranus, when they ran them through their algorithms, it showed that we should lose the star behind Uranus, but we didn't. So, did we get results or not out of this? Well, we didn't quite know what we got at that stage. We knew we'd got something, but we didn't know what it was. I hope you can see this graph because it's quite an important graph from Nature magazine. And this shows the actual level of the signal. This is where we put the eyepiece in to check things are all right. The signal's back, and then the star went behind something, light got blocked out, and then we got the signal back. So they've got the signal, and then we got a drop, and then we got the signal. And that happened again. We got the signal, and then we got a drop, and then we got the signal. So this is the sort of data change that we're looking for. This is the signal from Uranus, this is the signal from the star. So we've got a significant drop in there. But the question is, why is it changed? Why did this happen? So the starlight was blocked out and then it came back. We figured the star didn't actually go behind the planet Uranus because if it had, the atmosphere would have gradually dipped the signal. And the other thing is the drops that we measured were quite a long way from the planet because we started at 4 o'clock in the morning. And so we knew we had something, but what was it? It was a bit of a puzzle at the time. Oops, here we go. So I was worn out and I went home to bed. Bob Millis went down and met the Airborne Observatory when it landed at Perth. And the first question that they asked him was, how many satellites did you see? And that's when we knew that those drops that we measured were actually real. So Millis and Jim Elliott, who was the guy from Kuiper Airborne Observatory, called a press conference, and they announced a swarm of new moons around the planet Uranus. And that's what we thought we had on the morning of March the 11th. We thought we'd found some new moons around the planet Uranus. If ever you're fortunate enough to go to Washington DC, I'm sure you would want to go to the Smithsonian Institute. And in the Smithsonian Institute that's put aside for science, this is a picture of the telegram. I know you can't read it, but just take my word for it. This is a picture of the telegram that was sent from the Kuiper Airborne Observatory saying that we think we've found some new moons. This is a printout of an announcement that Millis and Elliott made about finding new moons, and this was put out on March the 11th. These moons were 40,000 kilometres from the centre of the planet Uranus. So that's basically how we announced it on March the 11th. But there's more. The real results of this event didn't come for a couple of days, and in that time everyone cooled down and they were puzzling about these new moons. Well, Dr. Elliott, who was a very clever planetary scientist, he's no longer with us, noticed that the drops that the Kuiper Airborne Observatory had obtained on the star's way in behind Uranus were exactly the same distance as the star drops on the way out. So Uranus went in front of the star, so we had drops on the way in and drops on the way out. The data that we took from Perth Observatory corresponded to the drops on the way in, but then the sun had come up here, so we didn't get the other half of the event. So when they took the two sets of data and mapped them together, Perth Observatory data on the way in at the top, 1, 2, 3, 4, 5 drops in the data, corresponded to the data that was found from the Kuiper Airborne Observatory. But the Kuiper Airborne Observatory got the other side of it because they were over towards South Africa and they got 1, 2, 3, 4, 5 events on the way out. It was very unlikely that there would be 5 moons directly on opposite side of the planet. And so this symmetry could only happen if there was a ring of objects around the planet. And so that's what was postulated and later proven to be true. So by laying their strip charts out and then folding them in half, basically, they could match the data from one side going in and one side coming out. So another press conference was called 3 days later because it took that long to get it all together, and they announced the rings around the planet Uranus. At that time, in planetary science, there was only one planet with rings, and we know what that is. Saturn. So they had another NASA news conference, and we announced rings around Uranus. In Western Australia, on the other side of the world, this didn't draw any attention whatsoever, except from us people at Perth Observatory who said, wow, you know, we've done something, but nobody else really cared. So the original ring system that we observed, something like this. The bright one is the Epsilon ring, and there was 1, 2, 3, 4, 5 that we observed quite well. This is an image taken by one of the Voyager spacecraft showing a whole band of rings, but you can see the sort of various concentrations there. So this was verified several years later. Excuse me. Meanwhile, planetary thinking was changing. We'd always thought that planets were formed in this way, and some of them had moons. No one thought that planets would have rings. Saturn has rings, but they're mostly gas. And so that was all right, but none of the other planets were expected to have rings. It turns out, we know now that the planet Neptune, which is fairly similar to Uranus, has 3 rings, but they're not complete. They don't go all the way around. And we know also that Jupiter has rings. And these have also been verified by spacecraft. So during the 1980s and the 1990s, it became really popular to follow up these observations and find out if we could find more rings around these planets. I did another one here in 1983. There were several that we tried from Perth that were thwarted by cloud, but the one in 1983, that's the one I want. So this is the sort of thing that we got with a strip chart, and if you see the strip chart inside, you can imagine what it's like. You get a level of brightness, and then all it is a drop like that in your signal. And that was the actual observation of another one of these rings in 1983. Okay, well now we know that Uranus has 27 moons. We know that it has 13 rings because they've been discovered by other occultations and other flybys by various spacecraft. Thanks, man. Well, having said this much about how important this event was, I wouldn't be complete in this talk if I didn't tell you about some of the other important events that have happened at Perth Observatory over the last 40 odd years. And I'll just list them quickly here, but I'd just like to explain a little bit about them. In 1986, observers including Craig Bowers on the 61 centimetre telescope found gas jets coming out of Comet Halley that caused Comet Halley to spin. And this led to revised information about how Comet Halley was evolving. It was discovered at Perth Observatory. Nobody else found this. 10% of all the positions on Earth of Comet Halley were taken with the astrographic telescope here. It was really great because Comet Halley went so far south, it was up there around Alpha Centauri, that we could actually get it in the south, and there's not too many observatories in the south. The catalogues of stars that were done on the Meridian telescope, and there's some Meridian telescope observers here tonight, were the basis of some of the catalogues of stars that are used by spacecraft for navigation these days. In the 1990s, people like Andrew Williams, who is here tonight as well, automated the 61 centimetre telescope and searched for supernova, and they've been successful in discovering over 30 supernovae. 29 new asteroids were discovered between 1970 and 1999, most of them on the astrographic telescope, some of them on the 61 centimetre. Perth Observatory was in the top 10 observatories for a few years for positions of objects around the world, and basically that was taken over by automated telescopes after that. And The super-Earth exoplanet was also part discovered by people on the 61 centimetre telescope. So we've done a lot at this little observatory here in the hills. It shows what a little observatory can do if you've got the equipment to do it and the people who are willing to try. Because I tell you what, it's tough being an astronomer when you have to work nights all the time. It's a lot easier these days with computers where you can tell the computer to go and work, but working nights is interesting, as I'm sure some of you as shift workers know about. So, despite the fact that the government has decided not to do research science anymore, Perth Observatory, as you see it today, has survived. It's still providing astronomy to the people of Western Australia. Thanks, Melody. No, I need you. I would be remiss, just go back one, I would be remiss without mentioning these two gentlemen who are basically responsible for this. Jaime Spiegel and John Harris were government astronomers in the times mentioned up there. They were fine statesmen and they argued with governments and they set up this establishment here at Perth Observatory. So they set the foundation for the establishment of this observatory, and we really owe a lot to them. Thanks, Matt. The next one. I'd just like to end my talks with this. Astronomy is looking up. You look up, you can do astronomy. Thanks very much.